So one reason I want to cover matrix computations with MATLAB is because in the next sections we will need to do more significant calculations than what we did before. Also, in practice, usually we have much larger matrices than what we can handle by paper and pencil. Also, even for small matrices, you can double check your answer using MATLAB. All right, so let's see what we can do with MATLAB. So the MATLAB prompt has these double inequality signs. And the assignment will be on web work, and it will involve some larger matrices. You don't have to enter these matrices one by one, entry by entry. Most of these should be done using copy and paste. What's of course very dangerous with copy and paste is that it's easy to miss things. Especially I noticed that when I copy and paste matrices from web work, it's easy to miss these negative signs and the 1-1 entry. So please pay attention to that. Also, when you paste this into MATLAB, the syntax is similar than what you see in usual web work matrix problems. That if you want to specify the A matrix, you name it as A equal and then open bracket. Of course, the opening size, the size of the bracket doesn't become as large as in web work or as in printing. Then you paste the numbers, and the numbers should be already pasted when you use Ctrl V and Ctrl C in a rectangular matrix way as it's shown. Then of course you also have to find the end of the matrix and close it with a close bracket. Then very important technical issue with copying things from web work is that the first row, somehow the bracket becomes these strange symbols that is garbage for MATLAB. So you have to find the first row in the matrix in MATLAB and delete the garbage from the end of the line. And then you can go back to the end. Actually, you can also do it even from here. Once you completed the syntax, you specify that A equals open bracket, then the matrix, then close bracket. You can just press enter. And of course, MATLAB shows you again what the matrix is that you entered. Again, pay attention to 1-1 entry and the negative sign. It's easy to miss. Then the second matrix is B. Let's copy. Stop at the end of B, of course. So this will be B equals open bracket, Ctrl V, close bracket, go back to the first line, end of first line, erase the garbage. Make sure all the garbage is erased. And then enter. Also notice that on the right hand side there is a workspace that lists the information that you entered already, the variables. If you increase the size of that, let's see if I can increase it. Yeah, it says that it's one matrix 7 by 9, double is the precision, 9 by 6 is the other size for the other matrix. And then the C matrix. C equals open bracket, Ctrl V, close bracket, erase the garbage from the first line, enter. And let's see, C. I think I did something wrong. I entered 2 open bracket, so this is not correct. Let me re-enter it. C equals open bracket 1 open bracket. Oh yeah, so it looks like that I accidentally copy and pasted also one of the open brackets. So I got two open brackets. That doesn't make sense for a matrix. So close bracket, erase the first line, garbage, and then enter. Yeah. So if you want to check what A is, you can just type A, enter, B, enter, C, enter. And then you're supposed to calculate A times B plus 5C. So that goes simply saying that you have to type out the multiplication sign, the star, A times B plus 5 times C. And that should give you a matrix. And unfortunately, copy pasting back doesn't work for the whole matrix. You do have to enter it one by one. Yeah, so let me try to do that as fast as I can. Minus 23, minus 86, and so on. Tab works to go here row by row between the entries. Minus 161, and then I tab to the next one. Minus 57, tab, 161, tab. And once you are ready, you have to submit your answer, and it will show whether it's correct or not. If it's not correct, double check whether you entered it correctly or not, everything. And you should also check again. These initial negative signs are easy to mix with copy and paste. Next question. Again, the matrix is ABC. Now you have to calculate A times B transpose plus 4C. So let me copy and paste. You can rewrite the previous matrices. So I can redefine A, B, and C. If you try A times B plus 4C, well, there are several things here. So 4 times C. It mentions that inner matrix dimensions must agree. Also, if you try 4C, that doesn't work. It even tells you that, did you mean 4 times C? So you do have to write out the multiplication sign. And so the problem is, of course, that the size of the matrix, and you can check this with the size command, size parenthesis A, 4 by 8, and the size of B. You can use the up arrow to go to the previous commands. If you press the up arrow, for example, if you want to check size of B, it's easy to go to size of A back and replace A with B. So you have a 6 by 8, and you cannot multiply a 4 by 8 and a 6 by 8 matrix. But if you transpose B, then you get 8 by 6, and then you can multiply. The transpose is done with the single apostrophe in MATLAB. So A times B transpose plus 4 times C is what we need. And yes, we have a matrix there as a result, and it matches the answer box for the size of the matrix in the answer box. And again, we have to enter these one by one. So don't try to do this by hand. You have to use a computer. You might want to try mathematical, but I advise against it. It's really not for matrix calculations. You can do it, but not as nicely, not as easily as with MATLAB. The name MATLAB stands for Matrix Laboratory. All right, so this is also correct. Next, you want to solve a matrix vector equation. So this has the form a matrix, then a column vector equals to another column vector. So let's talk about this. So this has the form A times X equals a B vector. Now, I mentioned before, let me mention again, we're supposed to solve this using Gauss-Jordan elimination. And I also mentioned before, let me mention again, to write this, that the x is A inverse B. This is correct in theory, but bad in practice. I don't want to go into much detail with this. So this is related to numerical methods and also the finite digit arithmetic of the computer. So don't do this, don't calculate, don't solve a linear system using the inverse matrix. The way you're supposed to solve in MATLAB an equation like this is, well, if it was a real number, not a matrix, then you would divide through by it. So there is a so-called overloaded operation that dividing through with A, and it's from the left because the multiplication was from the left. You divide from the left, so it's A backslash B, like dividing B by A from the left. This is how you're supposed to enter it. Of course, we don't use the vector notation in MATLAB. So let's see how it works. We have the A matrix. Let's copy and paste it into MATLAB. And don't forget always to erase this garbage at the first line, at the end of the first line, but not the last entry. Then this is the A matrix, this is our B, the right hand side vector. You can also notice that it actually gets copied into MATLAB as a column vector. And then let's calculate x as A dividing B from the left. So it's A backslash B. And we get nice numbers. You're supposed to get nice numbers in these homework assignments most of the time. If you want to check, what you can do is multiply A back with x and then subtract B from it. So this is supposed to be 0. By the way, percentage sign creates a comment in your line to check the result. We can check what ax minus b is. And what you see is that this is not 0, but what you have here is some vector, column vector, with less than 1 in absolute value. And actually it's multiplied by this scientific notation. This is 10 to the minus 13 times those numbers. So this is pretty small number, very small number, but it's not 0. And of course the reason for that is that although our solution is supposed to be integer in these cases, if I choose format long and then I check what x is, you will see that this is not exactly 4. There are some non-zero decimal digits, and also like the 1, 2, 3, fourth entry is not exactly 4, it's 3.9999999. So this is all coming from rounding errors in the computer. Even though MATLAB uses double precision by default, still a simple, what is the size? A simple 10 by 10 matrix vector equation already creates enough rounding errors that you don't get precisely the solution. So unfortunately in practice you cannot get that. Maybe with Mathematica you can get the precise solution in terms of fractions. Yeah. So in MATLAB, since it's computer system, 1/3 is it doesn't have infinitely many decimal digits, so you're going to get a rounding error immediately. But in Mathematica, since it does computation symbolically, it might give you just simply fractions. And that's one problem with Mathematica, that you get a bunch of fractions that are pretty much useless. It's much nicer to see some decimal numbers, especially if these are integers. To go back to the shorter format of display, we use format space short. So let me mention again that the error was 10 to the minus 13. Now if you do that again, about now this time with the inverse that I told you not to do. So calculating the inverse of a matrix, it's inv parenthesis A, and then it would be, let me denote it with x2, inverse of A times B. So that gives you seemingly nice numbers also. If I use long formatting, then the result is similar, that it's just a bunch of numbers that are close to integers, but not exactly. But while this was the error for the Gauss-Jordan elimination with the backslash, if I, instead of that, if I now use the new vector that I calculated, the new solution with the inverse matrix, notice the difference. I'm sorry, what happened? Yeah, it was x2, not x1. So if I use this x2 solution, yeah, please check. In another example, I got actually worse error, larger error than Gauss-Jordan elimination. In this case, you cannot really see whether it's different or not. Both of them are 10 to the minus 13 size. All right, so anyway, so if you take this x, in this case, I recommend just using the integers. It's supposed to be integer, this one. So the solution is supposed to be 4, 9. Don't worry about the decimal digits. And double check for, that's not correct, 9 minus 7, 4 minus 1, 3, 4, 4, 3, 3. All right. Next example. You have to solve this equation that's about expressing a vector as a linear combination of other vectors. So we have one vector and we're supposed to write this as a linear combination of other vectors with some unknown coefficients. We have to determine what these coefficients are. So this is again from previous representation of linear systems that we talked about. Namely, if you have B equals let's say C1 A1 plus C2 A2 and let's say Cn An, that means B is a linear combination of the A vectors, then we can write this as AC equals to B matrix vector equation, where A is the matrix of the column vectors A1, A2, An. C is the column vector of C1, C2, Cn, and of course we have the B vector. So that means that to solve this for C, you would again do Gauss-Jordan elimination, and the way we do that in MATLAB is that A backslash B. This is simply a notation for Gauss-Jordan elimination. In fact, MATLAB has some additional tricks. It can notice the structure of A and in some cases do some tricks to avoid Gauss-Jordan elimination, but in general, the Gauss-Jordan elimination is what computers do. So this means that we're supposed to assemble the matrix A from these column vectors on the right. On the left, that's the B vector. B equals, copy and paste. Here is the garbage. So we have the B vector. Now, how do we copy and paste this into a matrix? One way to do that is that you start naming that A1, the first column, is the first column. Then A2 is the second column. And again, I made a mistake with the brackets. Let's see what happened now when I use two brackets to open and close the beginning and end of the vector. Yeah, it still looks okay. It's a 10 by 1 matrix, which is a column vector. Then one way to put together the A matrix is to just put together the columns like this in a row, column by column. A little bit faster way to do that is if you start using notation for the different columns of A. So to look at an entry like the 1, 1 entry in A, we just use parenthesis and 1, 1. So that gives you the -2, 1, 1 entry. For example, the 3, 2 entry is supposed to be 6. Let's check. A, 2, 3. Sorry, that's A, 3, 2. The third row and second column is 6. But then you can also do things like A, column, and 1. This is the first column. So what this column stands for is that all rows. And that means that once you have 2 columns, then to get the third column, you could actually specify that the third column of A will be this third column from here. So A third column is this. This is a new column. So what happens is that these matrices in MATLAB have adjustable sizes. You can increase the size by adding, for example, columns or rows to the matrix. Then the next column is 4. So now we have a 10 by 4 matrix. Let me also mention that if you want to check, for example, the last row, that means the 10th row and all columns, that will be the last row, -8, -1, -7, and 4. So we have 4 columns. Let's add the 5th column. Once you have all the 10 columns, then again, to get the C coefficients in the linear combination, we solve the A times C equals B equation using left division. So that means C equals A backslash B. And again, this is supposed to be integer what you get. 3 minus 1 minus 8, 8, and 9. And these are very nice homework assignments. Please note that in practice you will never get integer answers. These homework assignments were specifically created to give nice integer answers as much as possible. So the reduced row echelon form is used a couple of times. The comment for that is very simple. So again, let's create a matrix to work with. A matrix. And the reduced row echelon form, we use RREF. It is RREF also here. And these are also relatively, well, nice numbers, supposed to be nice numbers. A bunch of zeros, of course. You can notice that the pivots, where the pivots are, the last 2 rows are zeros. Of course, this is a very sparse matrix, a lot of 0 entries. What I recommend is to first enter zeros, because it's easy with the tab. Tab 0, and then once you fill it out with zeros, then go back and change the few non-zero entries. 1, 5, 1 minus 7. Also remember that, and then these ones going down diagonally. Remember that the reduced row echelon form is unique. You cannot argue that maybe your solution is correct. Also, the computer is pretty good in calculating all these big matrix calculations. And it's checked one by one, the entries. Next, the determinant. I mentioned before, at least to a few of you who were happy to use determinant, or I think one of you mentioned even in the introduction that you are eager to use determinants. No, we never use determinants in at least numerical calculations. There is problem calculating the determinant. It's not good numerical operation, prone to errors, numerical rounding errors. But otherwise, determinant, if you have a nice integer matrix with integer entries, then of course the determinant will be just a bunch of multiplication and division, or the subtraction, not division, and addition. It should be a big number. Don't forget to use format long for this, because otherwise you're going to have a huge rounding error since you don't see the last digits of the number, a large number. So MATLAB has a default scientific notation. You have to use format long to show longer digits, and then you can use the up arrow to go back to this determinant of A notation. Actually, this is still not good enough, or I'm not sure if it's good enough or not. At least it's not convenient to enter this because it's scientific notation. Here's a comment in WebWork that says if you use format long with double G, then it will be different. Yeah, then it will just give you all the digits that you can copy and paste. Compare this to the initial format that you saw, 1.1520 e to the 7. So a bunch of these entries were hidden because of the scientific notation. Next question. To calculate the inverse, well, I mentioned that you shouldn't calculate the inverse, but also you can if you have to for some reason. MATLAB can calculate the inverse if needed. And it's the inv of A. Now, probably you don't want to copy all these digits, the decimal digits, so what I recommend is to go back to format short. And then numbers are smaller. Of course, this is a 10 by 10 matrix, but I only ask for the one of the column, the fourth column. Now for that, what you can do is you can rename this matrix as B equals inverse of A. So now we have B, and then the fourth column is B parenthesis colon comma 4. Still, you cannot just copy and paste the whole column, but at least it's easier to find what to copy row by row, entry by entry. I try to make this matrix so that you don't have rounding errors too big to reach the tolerance in WebWork. And by the way, all these questions are written by me. Hope you don't find any error. Now, if you are a little bit suspicious that maybe WebWork accepts any answer, if you change one entry, this last entry, for example, 3.4 instead of 3.3, that's already not correct. So it does calculate the precise solution and tries to compare your answer to that. All right, so here's a second to last question. Column space for a matrix. You can do that in MATLAB in several ways. One is, let's copy and paste the matrix into MATLAB. Even Control X works. If you make a mistake, you can undo some of the changes. So here is the A matrix. 23 is the last one. This is correct. -6, first entry correct. So if you type help call space, it gives you actually the syntax. It also talks about sim, that stands for the symbolics package. If I type right now call space, then it complains that it cannot calculate the call space, the column space for double, because the A matrix has double precision numbers in it. You need to use the symbolic representation of A, and for that you have to create a new matrix, for example AA, and then type sim parenthesis A. So this is supposed to be some kind of symbolic representation of A. This is kind of the thing actually Mathematica does by default. It does symbolic calculations, while MATLAB mostly does numerical calculations. So the notation for the symbolic version of A is a little bit different because now it shows the brackets each row. Notice the difference between them. And now if I do call space of AA, that works and it gives you a matrix with 4 columns, and WebWork is expected 4 columns because it turns out that the column space has dimension 4. What's not convenient is that you have a bunch of fraction here, and that's coming from symbolic calculations. But this is actually not the column space that we calculated before. So this is just one possible basis. We already learned that we can have different bases in a vector space. So this is one basis, but the other basis that we use is a column space basis for the column space of A. The way I explained it is that it's supposed to be, it can be the pivot columns in A. So to get the pivot columns in A, we have to do a reduced row echelon form of A. Not the symbolic representation AA, but actually the original A matrix. And then what this gives you is that in the pivots we have the first column, second column, third column. This is not pivot, this is not pivot. And then 1, 2, 3, and the sixth column also pivot. So 1, 2, 3, columns 1, 2, 3, and 6 are pivot columns. And in my opinion, instead of entering these, you can try and enter these. These will work. In my opinion, it's easier to enter the original matrix entities. So 1, 2, 3, and 6. First column, second column, third column, and the sixth column. Actually, let me do it here. So A, column 6. And this doesn't do a entry by entry comparison since you can have different bases. It actually does a basis comparison. The last question, basis of the null space for a matrix. Now, if you remember how we calculated null space in a previous homework assignment, we had to solve the homogeneous equation AX equals 0, and then we had free variables usually, unless the null space was the 0 vector only. So then we had to write this with some free variable notation like s times one vector plus t times another vector, and these vectors were the basis vectors for the null space. So that wasn't a simple calculation, and there is no one actually simple step to do exactly the same way what's written here. What we can do is, of course, to copy and paste this matrix into MATLAB first. We definitely need this. And then if you do a help null, it talks about the null space. It mentions actually there are different ways of calculating it. If you type null A, it gives you 4, in this case 4 columns, and WebWork is expecting 4 columns because it turns out the null space has dimension 4. So the problem with this is that a bunch of decimal numbers, and once you start working with minus 0.0107, omitting the rest of the digits actually is quite a big rounding error. So what happens with this, that this null space that we calculate, the basis for that, if I just use this command null of A, this gives us normalized vectors. So the first column, for example, is normalized to length 1. If I do a norm, then I get that it's normalized to length 1. And each column is normalized. So it's a nice thing to have normalized vectors with length 1 vectors to work with. But then the problem is that it has decimal numbers. So instead of that, if you check the documentation of the null command in MATLAB, it mentions that if you use this option R, then this gives a rational basis for the null space, which is obtained from the reduced row echelon form. So basically this is exactly the way we did it. And I mentioned to you before, for the reduced row echelon form, also for the free variables, if you factor out numbers and get rid of the denominators, if you have some denominators, then you can get a nice basis for the null space that have integer entries. And that's exactly what this rational null space command gives us. Right? So let me say that null A, comma, and in between single quotes R, option R. So that gives a very nice basis that's easy to enter in WebWork. And again, it's mostly zero, so I recommend, well, but these vectors actually go column by column, so maybe we don't have to start entering zeros. We can just enter the first two non-zero entries and then the zero entries. And then in the next column, 0, 0, minus 4, 1, and the rest is zeros. And then the next column, minus 3, 1, and minus 2, 1. Right, so please go back and check the homework assignment in WebWork about null spaces, how we did it before. Again, you can double check with MATLAB, and for large matrices like this, it will be terrible to do it by hand. So make sure you know how to work these out. And again, in the future, in some cases, I might ask you to write out the calculations, but even then you can double check your answer with MATLAB.